Okay, so let's look at a hammer thrower has a ball moving off just off the ground and it's just going back and forth. So the hammer thrower has just got the ball going and it's at a velocity, it's at a constant velocity. I'm not talking about when they get the ball going and it's at a 45-degree angle and maybe it takes a go out into the field. I'm just talking about when it first starts and it's going in a circle. If we know a couple initial conditions, we can figure out what this velocity is. Initial conditions, we're going to use 9.8 meters per second squared as gravity. We're going to mass is 7.26 kilograms, which is about 16 pounds in the United States. And then we have a theta of 60 degrees. So there's a 60-degree angle between here and the Earth. And rho is going to be 0.93 meters. That's going to be our radius. So if we think about this, what's going to be the velocity of this thing as it goes in a circle? If we start out with the hammer, if we think about the hammer in the x direction and we think about the hammer in the y direction, what forces are going on with it taking place here? So if you have y and we have our x direction, what forces are taking place with the hammer? Well, number one, it's going to have a tension force coming up this way, and that tension is going to be at 60 degrees. Okay, so let's think about what goes on, the forces in the y directions. So let's just identify all my forces in the y directions. My forces in the y directions, well, I know that in the y directions there's going to be a tension here, but the tension's only going to be in the y direction. And if we look at this as being a right triangle, we know that opposite over hypotenuse is going to be the sine. So we know that tension sine theta is going to be one force that in the y direction that you're going to see or you're going to feel. The next force in the y direction is going to be the weight, which is going to be mg. So we subtract out the weight, which would be mg, and we know now that this is all the forces that we're identifying in the y directions. There are no other forces taking place in this thing. If the person swinging the ball would begin to slow down, gravity would begin to take over and the thing would fall. If the person swinging the ball begins to speed it up, the ball would take a travel towards the y. So let's think about that. That's going to be 0 equals tension times the sine of theta minus mg. Why is this 0? Because it's a constant speed, so the ball is not moving up and it's not moving down. So this is going to be our forces in the y direction. All right, let's think about our forces in the x direction now. We have this 0 down. Let's think about what's going on in this direction. So we also know now that there's also going to be a force in this direction. What's that going to be? Cosine, our tension times the cosine, which could be adjacent over hypotenuse. So I know the tension cosine now in my x direction. What am I going to be subtracting that from? There has to be some other force. Of course there's another force, because everything that travels in a circle, everything that has mass that travels in a circle has an acceleration towards the center of that circle. That acceleration is called the normal acceleration. The normal acceleration, by definition, mathematical definition, is this velocity squared divided by rho. And our rho is basically going to be our radius. So this is the radius, this is rho, and then it's going to be the velocity squared divided by rho. It's going to be our acceleration. A lot of people ask why, how can something have an acceleration this way and not fall in on itself? Why doesn't the ball go in? If you're being accelerated this way, it would seem like the ball should fall in this way. Well, let's think about that. So if you're in a car and you are accelerating in this direction and you're sitting in the seat here, you're going to feel the force pushing you back this way. As you accelerate this way, the force is going to push you back this way. So this ball is actually going to feel a centripetal force out this way. But that centripetal force is going to be the same as our normal force. Just like the more you accelerate here, the more you're going to be pushed back in your seat. It's the same principle over here. It's accelerating this direction, but it's being pushed out. The ball is being pushed out in that direction of the centripetal force. So this would be our acceleration in the x direction. So we know that our acceleration in our x direction is going to be mass times acceleration, which would be velocity squared divided by rho. And is this going to be equal to 0? Yes, because it's not moving in the x direction. So t cosine theta minus m velocity squared rho. This is all the forces that take place now in the y direction. I'm sorry, the f direction. All right, so now we have some some initial conditions and we have some unknowns down here. We don't know tension and we don't know velocity, but we have some initial conditions. Let's see if we can first find the tension. I'd probably use this formula because it's going to be much easier. So tension sine theta minus mg is going to be equal to 0. So my tension sine theta is going to be equal to mg. Therefore, tension is just going to be mg divided by sine theta. All right, well, from the initial conditions, we know m, we know g, and we know the sine of theta. So tension in this case is going to be mass, which is 7.26 kilograms times 9.8 meters per second squared, divided by the sine of 60 degrees. All right, now if we look at this, we could say, oh, kilograms meters per second squared, that's a Newton. This has no units to it at all. So I know that my tension is going to be 82 point something. 82.24. Good. 24 newtons. So now we have found the tension in the spring, or the tension in the in the chain up here. That's going to be 82.24 newtons. All right, so now we found tension. We can put our tension back into here and we can solve for our velocity, which is what we're ultimately after. We know rho, we know mass, we know the cosine of 60 degrees, and now we know the tension. So let's plug that in and just see what we get. So we'll find out what the velocity would be. Nice and easy. All right, so tension cosine theta minus m velocity squared over rho is going to be equal to 0. Probably the easiest thing we do is to subtract t cosine from both sides. We have negative m velocity squared divided by rho. It's going to be to negative t cosine theta. Well, we have two negatives, so we can just get rid of them. We don't like them. All we do is cause problems, so we'll get rid of that. So what are we going to do with m? We're going to divide both sides by m, so we have velocity squared divided by rho. It's going to be t over cosine theta. Well, we have rho here, so what we're going to do, multiply both sides by rho, so we have velocity squared is equal to t times cosine, sorry, there's an m over here, cosine theta multiplied by rho divided by m. And then what do I got to do? Take the square root of both sides. Now, in the square root, in this case, you're going to take plus or minus, but we're not going to worry about the minus side because we don't have any minus velocities over here, so we're just going to look on the positive side. So we have velocity is going to be equal to t cosine theta times rho divided by m square root. Again, we're just going to look at the positive side. We're not going to look at the negative side. And when you put all your numbers in here, we have t cosine, we have t is 82.24 times the cosine of 60 degrees times our rho, 0.93 meters, divided by our mass, which is 7.26 kilograms. All of that cancels out to newtons. All of that cancels out to meters per second, and we get a velocity of equals 2.29 meters per second. So there you go. It's not that hard. Don't get too worked up or thinking about what am I going to do? How am I going to solve this? It seems like it's almost impossible because I don't know much about it. But with those initial conditions, you can know a little bit about it and understand what's going on. Okay, so in the second part, I'll take this second part, and then we're going to find out how far the ball will go once the person starts swinging around. How far will the ball go out downfield at once with this kind of velocity? Thank you. I hope you subscribe.